Hi, I'm Abida, since we're being recorded. Today I'm going to try to talk about pi calculus, and pi calculus has to do with interacting processes, so that's why it's called pi calculus. The pi is for p, which is processes, and we're just going to build it up from the rules, and I'm going to show you how these rules are kind of built up and then how to apply them. And since things are processes, they can react with one another. So really, like, the first thing maybe to know is that we have these things with lowercase letters that are like using lowercase letters, that those are names. And then you have these certain rules, and it looks like a grammar. Like, in fact, it is. So we have null, and then there's a little bit of weirdness with some of the notation because this pipe right here, it means that two parallel processes are running. So that is actually a symbol in the grammar. I think that's why in this particular image, like, that's why plus is being used to indicate the different rules. But sometimes I'll use the parallel, like the pipe, to represent the parallel rules as well. I'll just try to note that they're like different things throughout. And so basically, when we talk about these rules, we have this kind of syntax where we have these names, like I mentioned. So this is the same stuff. And when you have this line on top of A, that's like we call it like the complement of A, although I think that word is maybe loaded. And when you see A with a bar on it, and then B, which can be inside angle brackets, it means to send the value B on A, and then it's got dot P, then do process P. And then if you see A without the bar, and then in round parentheses X, it means receive X on A, and then do P. So one is output and the other one is input. And so these are processes that are working together. So in some sense, like, if you see A and A bar together, it means that they're going to react in a process once I write down something a little bit longer here. So good. And so this is communication, right? So I said, so you have AY. I prefer to write it with the angle brackets. Either way works, but I think the angle brackets makes it a little bit more clear what's going on. This means that you can basically replace the Y and X over here. So this is like, because these channels interact with each other. So because it's A and A complement, they can interact. If you see letters in there that don't have their complement, they're basically unobservable. So I wrote here tau, just any letter, but just scroll up. Tau is unobservable because it has no complement. And the way that you can look at this as well, is you can think of these names, right? I told you N was like the names, but you can do it as union with N bar. And like, so you have A and A bar. So those names are either the letter or the letter with the bar on top of them. And if you think about it sort of like in a finite state machine sort of way, or a box, like an actual vending machine, maybe, the pressing like the letter A on one box means pressing like not complement A on the other boxes. So you can see here how like the black box A and B interact with each other because I have this B bar and B. And so if I press the button that says B bar on A, then it like presses the button B on the box B, right? So they go together like that. But here in this picture, A and C bar don't have a complement in the picture, so they're unobservable actions. And it would probably make more sense, even though that's like a true thing to write, maybe just replace that with B so that it matches the picture. So pi calculus, it's about concurrent processes. So we want to have a language that describes processes interacting with each other. One sort of like real world way to apply this is actually with like chemical reactions. So this is just a grammar that represents those like kinds of processes happening. And it surprisingly does a good job of describing like object-oriented programming and other sorts of things. So you can start out with like, here's like what's going to happen, and then you can actually apply the reaction rules like I showed you, and then it's going to say like this is going to be the outcome, and at the end you can say like, oh, I had this really long string at the beginning, but in the end all that's really happening is that Y is being sent over X or something like that. So you can do like reductions sometimes, reductions, I guess they're called. Yeah, reduce an expression, reduce. Okay, so because B and like complement B are interacting, you can think of it as like a handshake. So I already told you guys, like, if you see those both, then it means they're interacting with each other. And you can actually define like a set of rules. So you might say, look, I'm going to have like this system that I'm building up, and it's going to have these rules where I have, for example, A A prime, B, and B prime. And A is defined as like the action where like A gets sent on A prime, and then B is B on B prime, A prime is B bar on A, and B prime is C bar on B. And so the way that I drew this as kind of like a finite state machine is to show you that A, so you see this arrow that goes to A prime, and it's got little a on it, which is this definition right here. And then from B prime to B, I did C bar, right? Because those are those like two rules that I have there. So that's this rule and this rule. Now, I didn't draw the letter B, but what you can see is in the center there, I have these two sorts of arrows, and this is like because it's B and B bar, you can see that these two are going to be able to interact with one another, right? Because it's B and B bar. So when I press the button B bar on the box A prime, it's going to automatically press the button B on the box B. Yeah, there's two ways to think of it's like perform action. Yeah, good. So it's send B, then do whatever's in the box B prime. So like we don't actually, so that's why I called it a black box. I don't actually know what's going on in there. So this like B prime could be more complicated and have some actions associated to it that you might know from the rules, but I didn't give you any rules that look like that. The arrow is related to the dot because it's B dot B prime, which is this arrow being sent like on here, but it's a different sort of sending than the messages. This just represents a state of the system, the picture that I have here, but but there could be more something different about like what messages are being sent. We haven't defined semantically what the messages actually mean, right? It's like a good question, so maybe you can write it down and I can like give you like a more solid answer or give myself a more solid answer. If I had like another definition, let's say I said there's this process P, and P is defined as running A prime and B in parallel, right? So remember that pipe means running concurrently. Well, I can use these rules that were given above, and I know that A prime is defined as B bar A, and B is defined as B prime up here. And so if I put those in there, it turns out that like B and B prime, or sorry, B little b and B bar are going to interact with each other because they do that handshake, like I said. And so what ends up happening is like they talk to each other. So these two things can happen. It's all actions, it's all processes. These two things can happen. And so what I'm left with is A bar B prime. Like they kind of, in terms of algebra, it's almost like they cancel each other out. Like, do we believe that like B and B bar like represent like things happening, like an action? Because if you press the button B on one box, it presses the button B bar on all the other boxes, and then they disappear. But we're having a little bit of, and this is my fault, like we're having a little bit of muddling between like processes happening versus like the whole point of this is that we're going to be able to send messages on channels. But this part is just like the processes part. If you kind of believe it's like algebra, I think like things can cancel each other out based on like some rules that I'm showing you now, even if it makes no physical sense yet. Like we should try to see if we can like work out basically a problem. And so let's see if this actually works out the way that we think it should based on what I've just told you. Okay. So there's this concept of kind of non-determinism, meaning that this thing in the center can react with this on the left or this on the right. So you have two possible outcomes that you can get from this. Now, that's going to give me either y bar v y bar v concurrent with a bar z, or it's going to give me a bar y concurrent with z bar v. So do we believe that this should work? Let's work it out. So I see that this A, okay, let's do the left one first. And this A bar are here. And the rule here is we had that ability to basically replace Y with X everywhere in the system, right? I'll pull it back up. Like we had this rule here. So because I have A bar here and A here, then this Z just goes on top of the X, and then you put it in bars like that. It's like a replacement, or read X. It's optional, but you can put the angle brackets in there if you like. I prefer them, but I did it both ways. Okay, so basically this is what's called like a read X. This, because like Z is being sent, let's see, so let's think about it. Like Z is sent on channel A, X is received on channel A. So it basically, per the rules of the systems, it means that you can replace Z, X with Z, right? Yeah. I think that's right. So going back here, I see A bar and A. So that's going to give me Y on X. And that also leaves me with whatever X bar V was, which means that I'm going to replace, hopefully I said the replacement rule correctly, but I replace that X with the Y. So that leaves me with Y bar V if the left hand side occurs. Really took a long time to parse this out, like weeks, and I'm still not that good at it, so it's fine. Okay, cool. And then, so that's this non-determinism thing, so we can do the right-hand side as well. So let's just use purple, and then I see I have A and A bar again. So let's see what my rule is. Maybe I'll use green again, I don't know. So this means X, or Z, this should be Z. So this should be Z on X on XV, right? Okay, so then that's going to give me Z bar V, right? So that makes sense, right? Good. So right now, this is kind of like a mechanical process where if you can just see how to do these replacements, you can reduce the expressions. And then you can say, well, this has non-determinism, so I don't know which of these reactions is going to occur, but I know that this is one of the two possible outcomes. There's a couple of other rules, although maybe sorry, 1 second. I'm gonna go back to my other note, and we're gonna do, I have to zoom out further, like that. Okay. Oh, I see what to do. Okay, cool. So let's look at another example where I've given you a new rule, which is this word new, and you'll also see the letter new. So you can see this. But anyway, I have the word new here. And so new is a restriction. It means that it restricts what that variable is called inside that scope. So let's think about these reactions. Okay, and then I gave you also this one, plus. So as promised, there's a lot of confusing notation. Here, the plus means XOR, which means one or the other thing is going to happen. So if we look at the reactions, then you have whatever's happening in here. And because I have A inside the scope and then this not A, and this is this concurrent process, right, that's happening here, I can see that either that A Q1 can interact with A bar 0. Oh, and A bar, sorry, 0 is called the null process, which I did define at the beginning. So sometimes we don't write it. And then since this is an XOR, it means that the alternative choices in a sum are discarded. So if you write that out, then you will get, since AQ1 interacts with A bar 0, this should say A, all you're going to be left with is A dot Q1. Actually, and I left my book at home, I guess A is restricted to that scope, so I think you still have to write A. So this is part of the definition. So this whole thing right here is the definition of P. I'm just saying that's what P is defined to be, and then we're going to try to figure out what the reactions are from there.
Okay, so would all of that be on one line?
Oh yeah, if I had space, I would have written it on one line. Maybe I could, but let's see if I can pull it off. But oh, I didn't know it would squash. That's the best I can do. Oh no. Okay. Yeah, so that's all in one line. So that's the definition. That's just the definition, and then I'm going to just say what the reactions are going to be. So let's think about these new rules that I gave you, which are new and plus, aka XOR. I'm not sure if maybe I miswrote something. Do you guys think it's supposed to be new A Q1, or it's just supposed to say new A Q1 and I did the binding wrong? It's new A Q1? Because the A and the A bar should work together, right? And then they both get removed. Yeah, 0 does nothing. So if we go back to the rule, see the rule again? If you have something like this, it's just going to replace in that process, but there's nothing to replace. And then there's nothing left, which means you're only left with Q1, I believe. So I think I was correct to have one A, just one single A written there. So it's probably worth checking. Maybe I'll make I'll use red highlighting so that I'm afraid of it. And then I remember to check it. Okay. And then here, nothing is going to happen to this part. There's nothing for it to react to because everything happened on the inside of this new, because the B, I'm saying since the alternative choices were discarded, B Q2 didn't do anything. Now, the other option is for B Q2 to react with B R1. So if you look at this, you're going to see B Q2 and then this new A and A bar 0. And it interacts with this B R1. And so since the alternative choices get removed, that A bar R2 disappeared. And then also because I have this here and this here, I'm left with the process. Oh, I think there's like that should be B bar. Yeah. So you don't need to write the B. So you're just left with Q2 and R1, but that A bar is left over because it had nothing to react with, which probably help if I actually scroll properly on the page. And if you think about it, there's like a weird thing about like the first one because the A bar remained. Can you guys think about like why that is? Yeah. So right here, the alternative choices are discarded. So I agree with that. But in the first one, I used AQ1 and then A bar, but that's this part. I didn't say anything like I didn't discard either choice here. Yeah, like why doesn't A bar R2 disappear? Okay, so it disappears because in this case I did make a choice on this one and I didn't make any choices on the first one. You could continue and say like, well, there's two possible outcomes from here as well, which is like discarding this one or discarding this one, but these two are not going to react with each other. Like they're concurrent processes, but now they're independent of each other. Which one? Right, so these are two separate outcomes, first of all, right?
I'm wondering why there aren't.
Like I could continue one, right, to make two possible outcomes from that. And then here, you can't do anything more on one or in two. Because I said the thing that's going to react. So I said the thing that was going to react was BQ2 with B bar R1. And if B bar R1 reacts, that lets me remove A bar R2, right? And then let's see. So are there other possible, there's only two parallel bars, right? So either this guy reacts with this guy. Oh, I guess maybe there's one. Is there another possible choice? These are concurrent processes. These react together and these are bound together as well, right? Like, because they're in parentheses. So either the thing inside the parentheses happens or it doesn't. I think those are my two choices. And if the thing inside the parentheses doesn't happen, does it make sense for two to happen? So no reaction occurred with A bar, but since I did use this alternative choice, I did have to discard the first one. Well, B.Q2 can't react with A bar, right? So that leaves me with only AQ1 and A bar 0, which is 1. And then I say the thing inside there does not happen, giving me a different bar. And so now I want to say that those two react with each other, and those two can only react with each other if B.Q2 reacts with B bar R1. So that's like, I think when you simplify it, it's like these are the two possible reactions, essentially. Yeah. I mean, you can still be confused about one, but so let's think about this. So B, and I actually wrote out steps here. So BQ2 reacts with B bar R1. So I discarded the alternative choice AQ1 and A bar R2. But then this reaction just like doesn't happen. So it stays. There's like, there was nothing for it to react to. So it just stayed. Well, first of all, do I have like the right number of parentheses? 1, 2. Oh, 1, 2. And then this goes together, right? This is all with new. Can I like copy it? I can. Okay. And then if we go all the way down here, paste. Okay. So let's take a look at this and maybe let's try to rewrite it so that it's like a little bit more clear what's going on. So this is like this, right? And then let's like use this just to like just to visually differentiate what those parentheses look like. And so I don't need those if I didn't have this new here, right? So I could say P is equal to, but this is a different question, right? Plus B Q2, and that, yes, is in parentheses, barred with A0, barred with B R1, and I'm going to put that in parentheses, A to R2. Okay, now this is a different problem because the new did have a meaning, but maybe this looks more like this guy interacting with this guy or this guy, right? So let's say the left one happens. We agree that those two interact with each other, leaving us just Q1, and then the alternative thing gets discarded. And then this, like, nothing changed here, right? Good. And now I did change the problem because this A bar is now in the same context as this A bar. Oh, but they can't do anything, can they? Because they're the same letter. So I don't think that can reduce any further. But I think maybe something different was happening because you were asking about the parentheses. So now let's think about that. These were my parentheses, right? So either this has to interact with this, but the thing inside the parentheses has to happen first. Okay, so let's do that. Okay, so thing inside the parentheses, we're all in agreement that this like is the outcome if those two interact, or discarding alternative, I have BQ2 bar A bar 0, yeah? And that still leaves me with B bar R1 plus A bar R2, right? If I do that first one, now if I do the second one, and this is the interaction that I got, I will be left with B R1 plus A bar R2. And now these two are not going to react with each other, but this guy could react with this. So this part's like all together, but it kind of doesn't matter anymore that this is here in terms of reaction, right? So that leaves me with BQ2, which is going to interact with R1, which is just going to leave me with Q2 or A0, and then this alternative sum gets disappeared. So that should just leave me with R1. That's not quite true because the new actually did have a meaning, but I guess maybe to make that better, that's A prime bar. Oh, also it's like very helpful if like my screen is on there, which I'm apparently not very good at.
So I'm like really lost.
So what my goal with this talk was, first of all, to just show you guys the rules, like say that there are grammar rules that do these things, right? And these rules are relatively simple. Like I think I'm hoping everybody understood, like, hey, there are some rules and they have some meanings. So we like agree, like, you know, we send B on A, you receive X on A, you can do things in parallel, you can do new, which is also, I was writing as new. We didn't talk about replication yet, and then we can do this like XOR sum, right? So we agree that those are all the rules. And these rules, because of like the way that they're set up, have certain like outcomes that are associated to it. So if you just basically define a process as like some legal combination of this grammar that's being set up here, then you can now do some like rules to reduce it. So it's basically like, here's a grammar that builds up what looks like an algebra expression. And then if I have an algebra expression, I know different rules that are going to allow me to reduce that expression. Actually, applying those rules is quite difficult, which is like kind of the difficulty in this talk today. But I think these rules are very easy, like at least relatively easy. We know like from 6th grade how to build up algebra expressions. Like, okay, I can like put a plus, I can like add some parentheses, I can do this, and that creates like a legitimate algebra expression. Only like in 6th grade, what you're given is like you're given the expression that's pre-made for you, and then you are told some rules that allow you to reduce those expressions. And that is exactly the same thing that's happening here. Only this like sort of, these expressions represent processes which represent actually like sending communication across channels. So it represents something different than what an algebra expression represents. And I hope that like high level thing makes sense, even if like the sort of mechanical application rules don't make sense yet. So there were like these sorts of diagrams. Oh, and then there was a picture of a car, which I didn't actually look at, but we can look at. I can't explain it because I didn't actually look at it before. The capital letter P represents a process, but the little letters are names, which could also be processes. Like everything is a process, but you're like sending, it's all about like sending back and forth. I think I didn't answer your question at all, but it's sort of like, it's like kind of unclear what like the process actually does, unless it's to send more things, because P could be broken out further, right? I mean, which is what the grammar represents. Yeah, what does it say on my board, which I wrote? Yeah, I think they're just in circles because like you don't know what's going on with them, because all the parameters are just channels. They're literally like everything is a channel here. So when I say like send B on A, it's literally, here's like a channel that's like named A, and I'm sending B on it. But, oh, is that picture not appearing? Oh my gosh. Okay, yeah. I'm just gonna redraw it because that was, okay. So here, like this is a channel and its name is like channel A, right? And I'm gonna send the like name B on it. But B itself, like everything, like for the pi calculus, everything is a channel. So then like at the end, we kind of just get to this point where we have these capital letters, which are processes, which consist of more channels and more things being sent, but we just don't know what they are. Like, because that's just like the end of our recursion. And so we just kind of draw the circle, the big roundy circle, and we're like, something happens in there. Maybe it ends. It could end, but that's like not part of the grammar. But that would be like a meta syntax, right? Like at that point. So the metaphor that they were using in the book was like, literally think of it as like a vending machine. Like, and if you press like the button A, it gives you tea. And if you press the button B bar, it gives you like coffee. So that's like all it is if you have a single one. But then what makes it complicated is that now you have this vending machine where if you press the coffee button, it makes like something else happen. Whatever like complement coffee means. Get fee out of the other machine. I guess the thing that I was like trying to get us to with this example was going back here. So I explained the redex and all of that. Like the reason that like this A bar here doesn't react with this A here. Did y'all catch like why that was happening? It's not the same A because new binds A to a scope. So new A means something different because that's like in the parenthetical there. So that's like a thing I wanted to point out. But A bar,
Yes.
yeah, it does because it's inside the scope. And also A bar like is uniquely tied up with A, right? It's just complement A. A dot Q1.
Yes.
Yeah, so it also binds, it's also like a scope for that one because it's inside more parentheses. I think doing this helps. Like that's where the new A lives. And then this guy's like on the outside, so he doesn't apply. And that's what I was like trying to get you guys to answer. But then there were like so many more reasons to be confused about this example. So we didn't actually get to say that. Yeah. So yeah. So those, I guess like you can think of those lowercase letters as, you can think of them as like action prefixes, which means either sending or receiving a message, which is a name, or if it doesn't have a complement, it's a silent transition. We just like kind of don't know what's going on in there. And that's about it. Like, I think you guys like know pi calculus now. I'm sure you don't understand pi calculus, but everyone knows pi calculus now. Yeah, maybe that's like next week's 2 weeks from now seminar. So one of the like use cases, which I guess I have to do some reading, is this is using cryptography because cryptography is all about, you know what, I can talk about cryptography all I want. I don't even need to prepare. But crypto is like all that happens is like you have Alice and she like wants to like send messages with Bob. And so these channels have like some sort of like meanings, like, okay, let's say there's a group G. And she's a generator. Yes, you do like that. Okay. And she's going to do like that. A is picked at random from, you down with that? That's like fine. A is picked at random from ZP. The order of G is P and G is the generator. And so she's going to send A. I did that super fast, but this is like this little A, but this is just algebra. G to the A. Exponentiation. Yeah. And then she's going to send A. Bob's going to do the same thing with B. And now Alice can do B to the A. And Bob can do A to the B. And in the end, that's going to give them G to the AB. Right? And like, there's not really a point in showing you this example other than it's kind of cool. But I think you can, because this is like about messages, I think you can turn this into something that's represented with pi calculus, which I can't do right now, but I think you can. But this would be like a very simple cryptographic protocol for establishing the shared GAB, where because Alice has a secret and Bob has a secret, which is little a and little b, they can calculate this, but like somebody who's watching in the middle, right, cannot calculate G to the AB because it looks random. So I think that's the point.